This banana just fell.
But what made it fall? Was it my sheer willpower? I wish. This demonstration definitely would have been better with like an apple falling from a tree, but I don't have any apples and I'm a YouTuber. What do you expect me to do? Go outside and touch a tree? And yeah, I did eat that banana. It's a perfectly good banana. Why would I let it go to waste? Bananas are pretty weird when you think about it though. I mean, it's just like this nutritious, vitamin and mineral rich nutrient meat stuff that's perfect for human consumption inside this perfectly sealed bacteria resistant shell that's easily peelable and biodegradable, which makes it even better than some food wrappers in that regard. And it's also delicious. I mean, I don't really know what I'm trying to say here. This is a video about gravity, not bananas. Now, the question of why do things fall has been pondered for a lot longer than the release date of this video. One of the earliest and most popular examples is the philosophy of nature proposed by Aristotle about 2,000 years ago. Now, despite a lot of claims, Aristotle actually did believe in a round Earth. And in fact, the round Earth model predates the flat Earth model by about the same time frame as special relativity. It's often surprising just how advanced ancient Greek thought was. I mean, nearly 2,000 years before modern science, they laid the groundwork for atomic theory, heliocentrism, the Earth being a sphere. They predicted the correct size of the Earth, and they even predicted evolution. Now, Aristotle believed that everything in the universe was made up of 4 primary elements: earth, wind, fire, and water. Man, wouldn't that be easy if my periodic table series could just be 4 videos long? Now, each of these 4 elements has their own natural place in the universe. So earth is in the center, water is just above earth, air is above water, and fire, or the heavens, is the outermost layer. Now, Aristotle believed that everything wants to maintain its natural balance. So that's why when you drop a rock, it wants to go to the center of the earth, which is why it falls. Whereas when you light a fire, it rises up quickly, as it wants to reach the heavens. Now, obviously, a lot of this is incorrect, but you can't really fault him for not knowing about elements when they didn't have atomic absorption spectroscopy in like 300 BC. And actually, my main problem isn't with the fire, earth, wind, and water thing. I mean, he was kind of right. They're all kind of made of different things. The problem is that his theory didn't really explain gravity. I mean, there were no predictive models or mathematical equations that you can do to precisely determine how this rock is going to fall. Not to mention that buoyancy and things being more dense than others does not really explain gravity. It just kind of pushes it back another step. If you say that oil floats on top of water, that doesn't explain why the oil floats on top of water. It just explains that oil is being pushed down less than water is being pushed down by whatever force is doing the pushing. He also didn't believe that the force causing a rock to fall is the same force that causes planets to orbit around the sun. That insight wouldn't come for almost 2,000 years later in 1642 with Sir Actually, first we're going to talk about Brahmagupta, because why are there so many old white dudes in astrophysics? Brahmagupta was a 7th century polymath that wrote a bunch of books that are very difficult to pronounce, even written in English. Now, Brahmagupta believed that all objects are attracted to the Earth. so it's a property of all matter. He described it like a river flowing, which is a pretty horrible analogy. I don't even know what it's supposed to mean, really, but at least he did have an analogy, which means he probably somewhat knew what he was talking about. However, he still did not believe that gravity was the force holding the planets in orbit, and instead, that, as it was common at the time, he believed they were celestial bodies, similar to Aristotle. He might not have been 100% correct about gravity, but he did invent zero, so we're gonna cut him some slack. Alright, it's the moment we've all been waiting for. We're finally gonna talk about I got you good. I got you good. Oh man. You thought a quick we're just going to cover them quickly. Galileo was much closer to gravity than any of the previous attempts. He openly supported Copernicus's model of heliocentrism and believed that all the planets in the solar system revolved around the sun. He was also one of the first to realize that planets were physical worlds and not just glowing little specks in the skies. He didn't view gravity as this universal form of attraction. Instead, he believed that all the matter on Earth had the property of being attracted to the center of the Earth. And this was the same for other heavenly bodies like Jupiter's moons. Now, he was very much ahead of his time with his belief that the planets orbit around the sun via some natural cause. However, he believed it was a different force than gravity. What's that? Alright. Fine. Isaac Newton was born on December 25th, 1642, in Woolwich, England. Now, contrary to popular belief, an apple actually never did fall on Isaac Newton's head, and he probably didn't even watch one fall, likely just imagining an apple falling from a tree. However, it does make for a great story. I already briefly explained this, but the main distinction between Newton's ideas and the ideas previous to him were that Newton proposed that the same force of gravity that exists on Earth is equivalent in space and is what causes the motion of the planets around the sun. In fact, everything from the smallest pebble to the sun pull on each other in some small amount, and he called this fact universal gravitation. He was also one of the first theoretical physicists to actually have the math to back up his claims. I mean, I guess you couldn't really call people before him physicists, considering he basically invented the field of physics. But the point still stands. I mean, what else do you want me to say about this guy? He was a genius. The next 3 centuries of astrophysics were basically dedicated to just proving him right. But there's one thing that Newton failed to do, and that was explain what is gravity. What is this force that's causing everything to be attracted to each other? And this question would mostly go unanswered until 1 year into World War I, 1915. Einstein started with a simple question. What would it feel like to fall freely, with zero force acting on you, versus to be completely still? He reasoned that without any external reference, someone who is moving at a constant velocity that passes somebody who is sitting still would not be able to tell which one is the one doing the moving. Because from this guy's perspective, he just passed somebody going down. Whereas with the other guy's perspective, he just passed somebody going up. And if there's no external forces, you can't feel or tell the difference. This is known as the equivalence principle. The only time the equivalence principle does not work is when there is an external force pushing on one of the two objects. Or people. In this case, it was people. Humans are not objects. But if gravity was a force, as was thought at the time, then you would feel the acceleration due to gravity. But an acceleration due to gravity, without being pushed back on anything like the Earth, feels identical to a free fall, which means gravity cannot be a force. Okay, if gravity isn't a force, then what could it be? Gravity is the curvature of spacetime. You can think of it like a ball rolling on a trampoline. You aren't pushing the ball down. There's no rocket attached to the ball. It just naturally follows the path of least resistance.
Different directions. But there was a preferred direction. The disk it formed from had a slight preference one way versus another, and things going the opposite way got eliminated, and when it's all said and done, everything's going the same way.
We can also know this to be true due to the effect of gravity's influence on light. Light has no mass. It doesn't interact with any other forces. It is a force. However, under extreme conditions, light is affected by gravity. It changes paths. It does not change speed, but it curves around with the curvature of space-time. You can see this during a total solar eclipse. The sun has enough gravity to significantly bend the light of the stars behind it. However, the sun is so bright relative to those stars you can't see it. But during a total eclipse, the sun is completely blocked out, and you can just barely make out the light of those stars from behind the sun, which would be impossible if gravity was not bending that light's direction. Black holes do the same thing, except for their curvature is so intense that it absorbs all the light. It changes the angle so much that its only path it can follow is towards the black hole. Now, black holes were just theoretical until a couple years ago, when we actually took a picture of one. This is what a real black hole looks like. The very edge of our knowledge of space and time. Whatever gravity is, the answer lies in here.
Entropy.